let's say R1C1 is much smaller than R2C2, which is much smaller than R3C3. So this is the biggest one right here. So that means for a smaller omega, this term right here starts to compete with 1. It becomes on the order of 1 before either of these do. So this becomes on the order of 1 when omega equals 1 over R3C3. Okay, at that point, if these are much smaller, this still is close to 0, this is still as close to 0, and you've got 10 log of 1, 10 log of 1, which disappeared. Okay, so you only get the effect of this. That's what happens here. When you hit omega equals 1 over R3C3, this omega R3C3 starts to get bigger than 1. And when it gets sizably larger than 1, then you can start ignoring 1. And you get minus 20 log of omega R3C3. And that gives you a minus 20 dB per decade. All right, then a little while later, now omega gets big enough to make this term on the order of 1. And now you can't ignore this term anymore. And for the same reasons, when this gets bigger than 1, this just becomes omega R2C2. You can pull the 2 out and you have minus 20 log of omega R2C2, and that contributes another 20 dB per decade. This one's still contributing minus 20 dB per decade, but now you're adding an additional minus 20 dB per decade. Okay, then you get up to here with this really small R1C1, so omega's really, really big now. And omega R1C1 is now on the order of 1. Now you can't ignore this term anymore, and it also adds an additional 20 dB per decade. Okay. Special case, really handy in filters, is when R1C1 and equals R2C2, which equals R3C3. And when you do that, and the corners are right on top of each other, then you start off again with this term omega R1C1. This omega RC is much smaller than 1, then you can ignore all of these and you just start off with your 20 log of A1, A2. Then you get to the point where all of these hit the corner, where this omega R1C1 becomes on the order of 1. And now they all contribute minus 20 dB per decade at the same point, and since you're just adding them, you get minus 60 dB per decade. And this is how good filters are made. After this frequency, the signals are greatly attenuated. Before this, before the corner frequency, they aren't attenuated. This is a nice attenuation factor after your corner frequency. Okay, this looks like a typo 2. Oh, I see what that is. Okay, for the active region, let's go back to an example of an actual circuit here for common source. Okay, as I mentioned, these capacitors right here, capacitances, they are all of the capacitance that could possibly exist, but for a common source you can get rid of a few. For example, the source and the bulk. Source is connected to ground, bulk is connected to DC, so it's a capacitor between grounds. That disappears, so that one goes away. Another couple that goes away is this gate bulk. Again, when there's charge in the channel, the gate doesn't couple to the bulk, it couples to that charge. So this capacitance is ignored. The other one is the CGS, and you say, well, CGS stays actually with the overlap. It's CGD that disappears. Okay. So when you get that charge in the channel, let's fix this if I can. When you get that charge in the channel, the GD, when you get that charge in the channel, that charge is considered to the source. So you've got the overlap from the gate to the source, but you also have that the charge in the channel is considered part of the source, so you get a CGS. The one that disappears is this CGD, and this is also a typo, but it looks like a, I can't fix that right now. So it's just the overlap for the CGD. This would be CGD. Let's do this. CGD overlap. Okay. Okay, so it makes it a little bit simpler. So let's look at that. CGS, CGO, CGD. Okay. This is if you use the Miller effect, the rules for Miller effect. This is what your common source amplifier ends up looking like. You know that there's two nodes that move. There's V in and there's V out. So that means there's going to be two poles. And so just your quick, if you want to write up an equation really quickly, you write your gain, which is your GMRO. In this case, R is probably much smaller than RO, so it's been simplified here a little bit. And then you have two poles, one from your input, one from your output. And this frequency right here is going to be 1 over the RC of your input, and this is going to be 1 over RC of your output. And then you are done. Okay, so that's how we've been doing it. If you want to do a longer version, which gives you some new interesting information, you need to go through the small signal model analysis. So that's what I did here. I used KCL. I took V in, oops, do I have this backwards? Current into the node. I do have this backwards. Okay. Let's fix that. This should be, let's just do this. Okay. Okay, so take Vn minus Vn prime over Rs, that gives the current through there. Then you have a current through there, which is 0 minus Vn prime over the impedance of this node, which is 1 over Sc. And then you have the current coming in across CGD-O overlap, and that's V out minus Vn prime overlap. And you can do the same for the output node. If you take this second equation, solve for Vn prime, and replace it into the first equation, you can get V out over Vn. An equation for V out over Vn with all of the information in it now. Okay, and what you've gotten here that you didn't have in your last equation was this 0 in the numerator. So we'll look at that in a second. Let's look at the poles first. Since in this class we are going to limit ourselves to the method just mentioned, where you find the C at a pole, or C at a node, and the R at a node. You take 1 over RC and you consider that your corner. We won't go through all the calculations here, but if you really want to go through all of the detailed small signal model calculations, what you end up with is a pole at this frequency and another pole at this frequency. But we won't go through all that math right now. You're welcome to do it on your own. But what I'd like to, well, let's go through this summary of a pole. Again, pole is just a low-pass filter that attenuates your signal, and the ones that we have been looking at are left-hand plane poles, and that's because they are of the form 1 plus S over